Okay, this is going to be a video on the imaginary number I and complex numbers in general and how to understand them, and to kind of realize that the imaginary number I is not at all imaginary. I think that that's probably the worst name for anything in maths. So to build up the complex numbers, we should maybe think about building up all the numbers. So very primitively, where do the numbers start? They start with the natural numbers. We usually denote that with a n, a special kind of boldface n. So these are just your counting numbers, 1, 2, 3, 4, and so on. And then, well, what comes next? Well, we're missing all of the negative numbers. So we'd like to have things like the negative counting numbers. And both of these go on infinitely long. The integers just go on infinitely to the left and to the right. And then next, we'll have a think, what do we need next? So we're missing a heck of a lot of numbers between 0 and 1, and 1 and 2 between each pair of integers we're missing fractions, for example, like 1/2, 22 on 7, and 0 is still in there. So all of the numbers that we can form as fractions, like p over q, so one integer over another integer, are going to be written like this, and this is all of the rational numbers. Now, here's a question. If you line up all of the rational numbers, is it a line, or is it just lots and lots of points? So what does the set of rational numbers look like? Is it a line, a solid line, or has it got lots of holes in it? The answer is it's actually got an infinite number of infinitely small holes. It's missing lots and lots of numbers. So for example, if we wanted to solve something like x squared minus 2, let's say we've got the function y equals x squared minus 2, so we could graph that. So it's just the standard parabola shifted down by 2. And we could ask, if we're only looking at rational numbers along the horizontal axis, could we find a root? So essentially, could we solve to find the roots is to set y equal to 0? And we're asking, is there a solution to this? So we're asking, is there a rational number x such that when I square it, I get 2? Which is the same as finding a root of this quadratic. The answer is no. There is no rational number such that the square of that rational number is equal to 2. In other words, the square root of 2 is irrational. So that kind of alludes to the idea that it's this picture, and if we kind of graph the parabola that we're looking at here, it would be missing. Kind of going through one of the gaps in the set of rational numbers. So what we do is we fill in all of the, let's call them holes. And there's a lot of them. But when we do that, we get the real number line, and these are the numbers maybe you're familiar with. So there's some numbers that are real in the real numbers, but not rational. And we were just talking about one, for example, the square root of 2. Another classic example is pi. So all of these numbers, they cannot be written as a fraction, p over q. That's the point of them. And then you go, okay, well, actually, if we're working over r, then now we can find a root to this quadratic, x squared minus 2, because when you line up all of these numbers, you get, in fact, the real number line. So the real number line is actually a line now, and there's no more holes in it. We would say it's complete. There's no holes in it. So you might be thinking, well, then that's it, right? I mean, if we filled in all the holes, that's all the possible numbers. Well, let's think of an example where that doesn't work. Let's say x squared plus 1. Let's graph that. So it's the same parabola, but it's just shifted up by 1. And let's think, well, could we find any roots to this? Well, you can look at the graph. No, we can't find any roots. It doesn't even touch the x-axis. So, is that it? I mean, if we try and solve this, right, we get x squared equals -1, and we go, well, there's no solution to that, so we're out of luck. We don't have a number that squares to -1. Well, just like we said over here, no, that's not good enough. That's not good enough. We're going to create the solution by essentially kind of defining it. In some sense, we kind of define the square root of 2 to be the number that squares to 2. In the same way, we're going to define a number called I. We're going to define a number called I, which has this property that I squared equals -1. And this might seem like, well, that's not a real number. Show it to me. Show me what the number is. At least give me a decimal expansion or something. Well, I'm going to show you what that number is and how real it really is, in the sense of it's really no more imaginary than, for example, pi or the square root of 2 or 1/2 or even 1 and 0. In my eyes, the complex number I, the imaginary unit I, is just as real as these other numbers. It has a very strong geometric property, just like every other number has a geometric property. So the idea, at least before I get to that, is once we do that, we kind of want to solve things like x squared plus 1 equals to 0. That's another equation we could have made, which cannot be solved in the real numbers. And when we do that, we get what's called the complex numbers. Okay, and all we do is we just take a complex of real numbers, so two real numbers, x and y, but we will write them as x plus yi, and x and y are just two real numbers. So that's why it's actually called a complex number, because it's made up of a complex, meaning a combination of, or kind of attaching two real numbers together to form another new number called complex number. So I told you that I is just as real as any other number. So let's try and understand, well, if it's real, then what is it like? What kind of number is it like? What properties does it have? And how could we construct it? So the important thing is that I really can also be defined as the square root of -1. And you might say, well, there is no such number that whose, when we square root it, or the square root of -1, there is no such number that has that property. It doesn't exist. Well, that would be like coming up here and saying there is no number that squares to 2, right? Well, I mean, if you're just talking about rational numbers, yes, that's true, but why would we limit ourselves? So what we're going to do is we're going to say, let's think about a number that would have this property, that it's the square root of -1. So in order to do that, we have to think, well, what is -1? As a geometric entity, as something that has some kind of geometric operation to it, how do we see -1? So let's draw the real number line, and let's put 0 here, and here's -1, and here's 1. And we think, okay, well, if I use -1 as a kind of geometric tool or kind of transformation, it kind of does something to the real numbers. So let's see, if I take 1 and I multiply it with -1, I'm just saying what's -1 times +1? It's -1. So -1 takes 1 over to -1. What does -1 do? It takes what does -1 do to -1? It takes -1 and it makes it positive, right? -1 times -1 is +1. And what does it do to 2? It takes it over to -2. What does it do to -2? It takes it over to 2. And what does it do to 0? Well, nothing, right? -1 times 0 is 0. So it looks like there's this picture of -1, which, well, how would you try and think about how you would describe what that is? It is really a reflection, let's say about 0, meaning that the way that -1 acts as a geometric object on the real number line, or as a transformation on a geometric object, is by reflecting all the numbers across the number 0. Right, so 1 gets over when 1 gets reflected over to -1, -1 gets reflected over to 1, and everything, all the negatives become positive and vice versa. So it's a reflection. Well, we're about ready to understand what I is then. I is something which is, it's a square root of a, or the, I guess, reflection. square root of a reflection. So what would a square root of a reflection be? Well, I have to think a little bit more about what the square root is. Well, the square root is the number that if we do the square root of x, any number x, times the square root of x, in other words, if we do this thing, whatever it is, twice, what do we end up getting? We end up just getting x. So the square root of a number x is a thing, let's call it a number, I guess, that if we do that number twice, kind of seen as a geometric transformation, we get back that x. So what does that mean in the context of the square root of -1? Well, I want something that is essentially kind of half, not in the sense of addition, but half in the sense of multiplication, half of a reflection. So I, or the square root of -1, all it is half a reflection. So now what we have to do is we have to think about, again, here's the real number line, and we want to do something to that real number line, some kind of transformation, which if we do that transformation twice, it results in a reflection about 0. First thing to notice is that, well, it can't be just maybe multiplying by a number, right? Because let's say, I don't know, we try 2. If we do 2 twice, the net result is just multiplying by 4, which is definitely not a reflection. If we try -1, so if we try a reflection, well, if we do a reflection twice, let's see, once, and then twice, it's nothing. It's like doing nothing, right? We're back where we started. And then that happens no matter where you start. That's just the fact that -1 times -1 is +1. It doesn't do anything. So it looks like we have to go into the next dimension, in the sense of, no matter if we stay on the kind of with the positive real numbers, if we do 2 of those, they're just going to keep kind of doubling, right? Or if we do some kind of reflection, it's going to come back to where we started. So we need to kind of come off the real number line, and I want you to think for a second, maybe pause the video and think, what is half a reflection? What can I do twice that the net result is a reflection? Okay, the answer is a rotation by 90 degrees, or pi on 2 radians, a rotation by 90 degrees. All right, so if we do that, 1 will end up here. I do that rotation, and here's -1. And if we do it again, second time, our net result is that we've taken 1 to -1, and -1 to +1, which is exactly what a reflection does. And in fact, any number, if you rotate it by 90 degrees and then another 90 degrees, the net result is a rotation 180 degrees, which is exactly what the reflection is. So the answer is the square root of -1 is really a rotation by pi on 2, or 90 degrees, anti-clockwise. Now there was a choice here. What was the choice? Have a think about that for a second. What was the choice? I could have made another choice here. Of course, I could have said equivalently clockwise. Doesn't matter. This choice is either I or -I, right? The square root of -1 is either I or -I. So once you fix that choice, then you've defined exactly what the square root of -1 is. It's a rotation by 90 degrees. So next time someone thinks, or you think to yourself maybe, why are we studying I, the square root of a negative number? It's not real, it's imaginary. It's even called the imaginary number. The point is that this is just a symbolic representation of something which we can fundamentally, or concretely represent. It's just a rotation by 90 degrees anti-clockwise. And in my books, if anything, it's even a little bit more concrete than the square root of 2. Square root of 2, sure, we can write a decimal expansion, right? We can kind of start to approximate it, but you can never write down the true value of it. The only thing that we can do is use these symbols to represent that quantity, just in the same way that we can write symbols to represent this quantity, except this quantity can be represented exactly, very concretely, as a rotation by 90 degrees, anti-clockwise or clockwise.